Hello friends, welcome to my channel. Let's have a look at problem 1579 together. Remove max number of edges to keep graph fully traversable. So in this video, we're going to share a solution based on disjoint set data structure or unified. So this problem requires to return the maximum number of edges we can remove based on the statement of the problem, or return -1 if it's impossible for the graph to be fully traversed by both Alice and Bob. So in the problem, there are three types of edges. So type 1 edge can be traversed only by Alice, and type 2 edge can be traversed only by Bob, and type 3 edge can be traversed by both Alice and Bob. So here are three examples. So in example 1, so the return is 2. There are two redundant edges. And in example 2, so the return is 0. So there's no redundant edges. And in example 3, so the return is -1. So means that Alice and Bob cannot traverse all the nodes. So the constraint about this problem is as follows. So we are not going to go through every item here. So we want to point out that the number of nodes can be up to 10 to the power 5, which is a large number. In other words, we need to pay attention to the time complexity when we devise a solution. So with that said, let's look at the method. So the method here is based on the disjoint set data structure. So the idea actually is very straightforward, though the problem is marked hard in Leetcode. So what we are going to do is the following. So we simultaneously construct the tree for Alice and Bob by first using type 3 edges, and then we use type 1 for Alice and type 2 for Bob, respectively. Here, the graph structure tree comes into play because of the problem statement, because tree contains the minimal number of edges such that we can traverse from one node to the other, right? So in the process, we're going to count the redundant edges for each. So in the unified setting, redundant edge is an edge that does not produce effective union. So with the idea went through, let's give a quick walkthrough for example 1 to fix the idea. So this is the input for example 1. First, we're going to classify the edges into different types, 1, 2, 3. For example, here, type 3 edges are 1, 2, and 2, 3. And type 1 edges are 1, 3, 2, 4, and 1, 2. Type 2 edges contains 3, 4. So listed here. Then we're going to set the result variable to be 0, where here we're going to return its final state. So for Alice and Bob, if we look at type 3 edges, so because if we look at 1, 2, so we get a cluster of nodes 1, 2. So there's no redundant edge, so the results remain 0. And when we look at 2, 3, then we get a cluster of nodes 1, 2, 3. So the result remains 0. Similarly for Bob. Then after we traverse this type 3 edges for Alice and Bob simultaneously, then we're going to look at type 1 edges for Alice and type 2 edges for Bob. So if we look at 1, 3 for type 1 edges, then we're going to get a cluster 1, 2, 3. It still remains. And 1, 3 are already in the previous state of clusters. So the edge 1, 3 is an redundant edge. So we're going to increment the result state by 1. So now the result is 1. And then if we look at 2, 4, because 4 is not in the previous state of clusters, so this edge is not an redundant edge, so it forms a full cluster of all nodes. So the result state remains as 1, and then we formed the tree, so that's good. Then if we look at 1, 2, because both 1 and 2 are already in the cluster, so this edge is another redundant edge. So we're going to increment the state of result by 1. So the current state for result is 2. So after we examined type 1 edges for Alice, we're going to examine type 2 edges for Bob. So note that after we looking at type 1 edges for Alice, the result state is 2. So now if we look at type 2 edges, that is 3 and 4. So this 3 and 4 produces an effective union because 4 is not in the previous cluster. So we're going to get the tree, and we have no increment in the result state. So the result state remains 2. So the conclusion is that both a tree is formed for both Alice and Bob. So the return is true. So that's the quick walkthrough for example 1. So you can actually walk through example 2 similarly. So with that said, let's carry out the program. First, I'm going to implement the disjoint set data structure as our tool. So actually you will see after we have the tool at hand, the problem is very routine or straightforward. And after we've implementing the data structure, so we're going to connect with the problem and quickly write down the solution. So with that said, let's first do our implementation of the DSU. So for that, I'm going to implement a class outside the class solution class, so this implementation can be used in other problem setting. So I'm calling it DSU, and then let's look at the initialization. So here I'm going to directly initialize the number of nodes because in the problem the number of node is a priori known. So here I'm going to n nodes, and then I'm going to initialize two dictionary. One called root, which stores the node and parents relationship. So it's I and I for I in range. So I'm going to count from 1 based on the problem statement. So n nodes plus 1. And then I'm going to initialize a rack. So this rack, we're going to use it for aiding the union operation. Initially, it's 1 because it's represents each of the nodes represent a single node cluster. So with that said, we are done the initialization. Let's look at the find function. So I'm going to use an I. So here the I is going to be a node. So represented by integer like a 1, 2, say n. So this, because we already add this I in the roots, so we just need to do the recursive call. So not recursive call, iterative call. So let's do first set this result by I. Then I'm going to check. Here, let me also use path compression. So we're going to check if result and its roots are the same. If not, we're going to iterate. So first, I'm going to add the results state to path, and then we're going to reset the result to be its roots. So after we exit this while loop, we're going to have a state that is result equals its roots. So we're going to return the result. Before that, let's do a path compression. So for node in path, we're going to set the roots of the node to be the result. So that's about it for the find operation. So now let's quickly do a union operation. So self ij. So basically we're going to check if I and j are in the same cluster. If they are not in the same cluster, we're going to reset the state, the root. So root I, root j equals self find I, self find j. Then we're only concerned if they are not the same. If they're not the same, we're going to set the roots. We're going to first track the rec information. If self recs root I is larger or equal than the recs of root j, what we're going to do is we set the roots of root j to be root I, and then we increment the rec of root I. Let's copy this line and modify it. So in the other case, we actually do the same thing, but in a reverse direction. Let's copy these two lines, and then let's set the root of I, to be root j, and then we are going to increment the rec of root j accordingly. So that actually finished the unit operation. So in order to suit this problem, we're going to implement another simple function called is sim root. So we're going to see if two nodes are in the same cluster or not. Basically, this is just a self find I, self find j. So that's about it. Basically here we are checking if they have the same delegate in the cluster. So this actually finishes the implementation of the data structure. So now let's look at the problem logic. So I'm going to split the process into different steps. First, I'm going to group the edges by type. So this is actually easy to do, edges by type. So I'm going to use a collections default dictionary. So the container I'll choose list, so that I can see the same order, using same order when we look at the type 3 edges for Alice and Bob simultaneously. So then we're going to traverse the edges for canned and UV in edges. Then we're going to do edges by type. Then the canned, so append this UV. Here I'm using a tuple. So that's about it. Now what we want to do is instantiate it DSU for both Alice and Bob. So let's see DSU Alice, DSU Bob. So it's DSU. So that's it. So now let's do the real work. So what we want to do is that we first, as we specified above, initialize a result variable whose final state is what we want to return. Initially is 0. Then we're going to traverse the edges. First for type 3, for UV in edges by type. So type 3. For type 3 edges, so we are going to use them to build trees for Alice and Bob simultaneously. So then we're going to do like this. If DSU Alice. So I'll check if their UV are in the same cluster. So if so, we're going to increment the result state by 1. Otherwise, so as long as one of Alice or Bob need to use these edges, or we're going to do the union for both Alice and Bob. So we're going to DSU Alice union UV. Similarly, DSU Bob union UV. So here's Bob. So that's the simultaneous scan part. So now let's do it for both Alice and Bob, but respectively. For UV in edges by type. Here I'm looking at type 1 edge. So we're going to check for Alice, DSU Alice. So I'm going to check if they are the same root. So if so, it means that UV edge does not produce effective union. We're going to increment the result variable by 1. Otherwise, we're going to do the union operation. So DSU Alice union UV. So that's it for Alice. So we're going to do the same thing, actually parallel for Bob, for UV in edges by type. Here's type 2. That's type. Then we're going to check if DSU Bob same root UV. If so, we are going to increment the result state by 1. Otherwise, we are going to do the effective union. Bob union and UV. So that's our main work. So finally, basically, it's a check and return. So according to the statement, we're going to check if for Alice and Bob, there are only one cluster formed. In other words, it both formed a tree. So for that purpose, I'm going to get the clusters for Alice. It's going to be, we're going to check the set. So in order to get the clusters, we just need to get its delegate or representative. So DSU Alice find I for I in range 1 n plus 1. That's it. Similarly, we can do for Bob. So it's going to be a set. So DSU Bob. So find I for I in range 1 m plus 1. So that's it for tracking this number of cluster information. So the return now is actually straightforward. So we want to check if the clusters for both Alice and Bob contains only one element. In other words, each corresponding to a tree. If so, we're going to return the result. Otherwise, we're going to return -1. If length cluster Alice equals 1 and length of clusters Bob equals 1. So otherwise, we're going to return -1. So that's the full code for this problem. Let's first do a special case check. So missing var required variable n nodes. So let's here. When we do the initialization, we're going to use this n and n. It passes the first example. Now let's look at the generic case. it passes the generic case. So let's give a quick overview or summary for this video. So in this video, we actually give a solution for the problem using union find or disjoint set data structure. First, we implemented the data structure. So mainly consider two methods, find and union. And then we connect the data structure with the current problem logic. And the solution for this problem are split into different parts. First, actually we group the edges by type, and then we instantiate the DFU for both Alice and Bob. And then we traverse or build trees for Alice and Bob simultaneously using edges of type 3. And then we look at edges of type 1 for Alice and type 2 for Bob. And finally, we check if a tree is formed for both Alice and Bob. If so, we're going to return the final result variable state. Otherwise, we return -1. So that's an example of applications of the disjoint set data structure. So you are welcome to look at the other videos in my playlist in the channel, or share the videos with your friend if you find this video is useful. Thank you very much.